then I'd like to go ahead and talk about equations and the balancing thereof. Now, this is a topic I'm sure you already have significant skills at. You couldn't get through high school chemistry without balancing equations, right? Am I correct? This will be review, but it is important review, and I ask that you keep a close eye on what's going on. Chemical reactions occur atom by atom. Okay? If you take 1 gram of A and 1 gram of B, and it happens to combine to give 2 grams of AB exactly, and I emphasize happens, that took place because a very large number of A plus B reactions took place, and it all added up to the total product that we got. In order to represent that chemical change, we use a chemical equation, and the chemical equation must be balanced. That is to say, the same number of each type of atom must appear on both sides of the equation. Okay? Reactions occur atom by atom, so none of these atoms are going to get lost. Whatever you've got to start with in the reaction, you're going to have at the end, unless we spilled some somewhere. Okay? Well, a long time ago, I haven't seen any of these in a long time, there were things called flash bulbs. And flash bulbs had a glass or plastic envelope, and inside the envelope was a bunch of very fine magnesium wire. And you can't see it, but this whole thing was pressurized with oxygen gas. And this was inserted into your camera, and an old-time camera, none of the new cameras have this that I know of, was inserted into the camera, and if the batteries were still good in the camera, when you flashed when you took a picture inside, this reaction between the magnesium and oxide would occur very rapidly and produce a bright light to illuminate your picture. Okay? So this is a chemical reaction, and when it's over, you see a white substance lining the inside of this glass or plastic thing. There are a bunch of burn spots here to indicate that this got mighty hot. If you put your hand on one of these right after it flashed, you regret it. There's a lot of heat released, but that's Chapter 6 material. We'll get there a little later. So the reactants were magnesium solid and oxygen gas. Oxygen is one of the 7 famous diatomics, so it's O2 as an element. And if we had the right combination of these reactants here, we would produce, according to the law of conservation of mass, the requisite mass of this product, magnesium oxide, this white stuff. So what we want to do is represent this chemical change with an equation. And we start off doing that by transferring the chemical information, the chemical statement that we just saw, into a skeletal or skeleton equation. The skeleton equation gives the reactants and the products, but it's not a balanced equation typically. Okay? This one isn't balanced. As you can see, there are 2 oxygens on the left and only 1 oxygen on the right. So our job is to find out what balancing coefficients go in these little spots for each one of them. Now, if it turns out that a balancing coefficient of 1 is found for any one of these, we'll leave it out. If there's no balancing coefficient there, we'll assume the presence of a 1. But otherwise, we'll put the numbers in, and the numbers need to be whole numbers. Again, until we get to Chapter 6, and then we can play a little looser with this. But until we get to Chapter 6, these all need to be whole numbers. So this skeleton equation is the place to start, and as a rule of thumb, it's a good idea to pick the most complicated thing to work on first. So what I mean by that is I would look at this thing and say, okay, we have to have at least 1 magnesium oxide, right? Can't have less than 1. You might have more, but you can't have less. So we could put a 1 in here as a trial balloon, right? And the reason we choose the most complicated thing is that it affects the largest number of other things. It's pretty trivial here. We put a 1 right there, And that means that if there's one magnesium oxide product, there must be one magnesium on the left and one oxygen on the left as a reactant. Okay? So in order to get one magnesium, we just put a 1 in there. But in order to get one oxygen, we got to put a 1/2 in here, because oxygen comes in units of 2. Okay? So at this point, the atoms are balanced, but we're not done yet. That is to say, we have to get rid of this fraction, among other things. So here's our fractional equation with a fractional coefficient in it. We have to get rid of that, and we do it the obvious way. We multiply all of these balancing coefficients by the smallest whole number that we can, and produce whole number results. So if we multiply this by 2, the 1/2 becomes a 1, the 1 becomes a 2, the 1 becomes a 2, and we are home free, except that we need to get rid of this 1 here. We don't put it in. It's understood. And so the balanced chemical equation would be 2Mg, here are the 2Mg atoms in blue here, if you wish, plus O2, here's the O2, the pair of oxygen atoms in the O2 molecule here, goes to 2MgO, and there's 2 Mg's and 2 O's in there. So checking the number, it's always a good idea to check. You can easily lull yourself into a false sense of security here. 2 Mg's on the left, 2 O's on the left, 2 Mg's on the right, 2 O's on the right. Everything is balanced. Questions on the process? Okay, the process works the same for all of the possible equations we might have to balance. Okay, up to and including the last step of checking. Yes, go ahead.
Just balancing atoms and not charges.
We don't have to worry about charges for cases like this, but we will have to worry about charges later when we look at solution reactions. The reason for that is we are using molecular formulas here, or what passes for molecular formulas for ionic compounds. In other words, everything involved we see here. If in the case of solution reactions, we might get to the circumstance where we only write down what's called the net ionic equation. There are some other ions we didn't write down, and that's when we have to be careful. We'll get there. Hang on. So let's do a more complicated one so that you'll feel confident about this. Octane burns to form CO2 and water, at least on a good day. Write a balanced equation for this reaction. So the reactants are octane, C8H18, plus dioxygen. The products are CO2 and water, ideally. Okay? And so we want to write a balanced equation for this. So let's write down a skeletal equation first. C8H18 is our octane. It is a hydrocarbon. It is an alkane. Plus O2 goes to CO2 and water, and the balancing coefficients need to be entered there. So we should focus first on the most complicated thing, probably the easiest way to, look at the total number of atoms, and octane has a lot more atoms than anything else here, so it's a good place to start. Then use the information in its formula to balance the other things. And we start by looking at how many carbons there are in one octane. We must have at least one octane. There might be more, but we've got to have at least one. So in one octane, there are 8 carbons. And so that means there are going to have to be, at a minimum, 8 carbon dioxides. Because there's one carbon dioxide, one carbon in each carbon dioxide. Okay, so let's start there. 8 carbons on the left requires 8 carbon dioxides on the right. So we write an intermediate equation here, which isn't balanced yet, that shows one of these octanes produces 8 CO2s and an indeterminate number of waters. Now, you can tell we're going to find out the number of waters the same way, and we're going to look at octane formula and see how many hydrogens are there, because that's the only source of hydrogen. So all the hydrogen that's over here in the water had to come from the octane. All right? Now you can see there's 18 hydrogen atoms in one octane molecule. And there's 2 hydrogen atoms in every water molecule. So it's reasonable to expect that we could put a 9 in here and balance the hydrogens. Okay, here's the 9. And we now have balanced carbons, balanced hydrogens, but not balanced oxygens. Everybody comfortable so far? Questions? Okay. Let's balance the oxygens. We're going to look on the right. There are 9 oxygens in these water molecules. There's 8 times 2 is 16 oxygens in the carbon dioxide. So 16 and 9 is 25 oxygens on the right. In order to get 25 oxygens on the right on the left from dioxygen, we need 25 halves O2 here. Okay? Each one comes with 2 oxygens, so multiplying by 25 halves would give us 25 oxygens. But there's the fraction again, and we have to get rid of the fraction. And I think you can see the easiest way to do that here is multiply everything by 2. We have 2C8H18 plus then 25 O2s, and that goes to 16 CO2s, 8 times 2, and 18 H2Os, 9 times 2 here. Yes, go ahead. It is? I thought I fixed that.
The 16 and the 18 are on the top, and then the 8 and 9 on the bottom.
Oh, I'm sorry. I was aware of that, but I had a note that I had fixed it. I apologize. Would you please correct that on your notes to look like what you see right here? 8 CO2s and 9 H2O in this line, and 16 CO2 and 18 H2O over there. Don't know how that happened. Must be a brain cell that burned out somewhere. Okay. Does anybody have a question on making the equation balanced? Is there any way it can be simpler than what it is right here? No. This is as simple as it gets. Yes, go ahead. Well, certainly that's the case for all diatomics. But you don't always have to divide by 2. If it turned out over here that you, instead of having 25, you had 26, then you wouldn't divide by 2, 25 over 2. You'd multiply by 13. Okay? So I'm not sure whether I answered your question or not, but you have to let the products be your guide as to what you do with this. Don't assume anything. Just know that when you're done, all of the atoms must be in the same number on the left as they are on the right. That's the only thing that counts here. Okay. Now, what I would like to do is to add the check in here, meaning before you leave this, you check to be sure that everything really is balanced, because it's easily possible to go off the deep end and change something you weren't thinking about changing or not changing when you were supposed to. So what I mean by that is 2 octanes, 16 carbons, 16 CO2s is 16 carbons, 2 times 18 is 36 hydrogens, and 18 times 2 is 36, and then we have 50 oxygens both sides. That's a very important step. Otherwise, you're leaving yourself open to the balancing equation god, who might smite you down if you don't check your work. All right? Now, sometimes when you see an equation written up in your textbook, or maybe on one of my slides, you'll see some additional information. And the additional information is that C8H18 is a liquid, O2 is a gas, CO2 is a gas, H2O is a gas. So sometimes it's written with, for each one of these things, an L in parentheses or a G or an S indicating the state. That's not part of balancing the equation. Okay? And we don't necessarily expect you to be able to do that with all these things, because you might not know that octane's a liquid and not a gas, for example. But when you see it, it has that information. One other thing before we leave this. Let's suppose I wrote down 4 times octane plus 50 times dioxygen goes to 32 CO2s and 36 H2Os. That is a balanced chemical equation, but is it an acceptable one?
No.
It's not acceptable. Why not? That's right. We can make it simpler by dividing by 2. You always want the simplest one with the lowest set of the balancing coefficients. And there are problems in the homework and in the practice test, and there may be some on the exam, that give you some choices of balanced chemical equations, and you have to go through and sort out the right one. So don't stop once you've determined that a particular choice has the atoms balanced. Make sure there's not a simpler version of it that you can get by dividing by 2 or 3 or something. Okay? Is that clear to everybody? Okay. So, balancing equations is a matter of carefully following the procedure. It doesn't have to be done in any given way, but ultimately you need to come out with an equation which satisfies this conservation of atoms.